Hey guys, welcome to an online video lecture. Right, super exciting. Um, this video I'm going to be covering Chapter 8, Section 7, which is integration by tables. We jumped over this in class the other night. Um, it's just this one's an easier one, I think, to go over online rather than in person. There's not a ton of new content here. It's just kind of another technique we'll be discussing. So, move that out of the way. So, yeah, I guess first thing is just to say this isn't going to replace any of the techniques we've already covered. I know many people kind of think this is like I don't want to say a one size fits all approach to never having to integrate again. That's definitely not going to be the case. You're still going to need to be familiar with all the integration rules we talked about so far. Just regular power rule, U sub, integration by parts, inverse trig functions, partial fractions. The whole gamut of stuff we've already discussed. But this is going to be a pretty useful tool to maybe saving you some time on some of these more complex integrals, right? So we've seen how I think the biggest thing I've tried to stress as we've been doing this is that the the integration techniques themselves are usually not terribly difficult to execute once everything is kind of set up in the right form, right? If an integral is able to be integrated by power rule, you guys can handle that. If an integral sets up really nicely for U sub or really nicely for integration by parts, you guys can go through the procedure and handle that without a ton of difficulty. The problem lies, as I've said, is when you get to a complex looking integral and you're like, where do I begin? How do I do this? Where do I even start? So this technique, integration by tables, is say a shortcut maybe, or it helps you go in the right direction. Now, many of you, I'm hoping at this point, have looked into Appendix B in the table, which lists, or excuse me, independent Appendix B in the book. There we go. Which lists all these integration rules that we will be using for this section. So, if you haven't, check it out. I'll actually link to it real quick. Actually, maybe I don't know. But it's actually. Yeah, I can actually do that really quick. Display capture. Oh, no, I don't want to do that. Window capture. I want to do a window capture. Window capture. Okay. Let's do review. There we go. Ta-da. So if I pop over, yeah, you guys can see that real quick. This is what I'm referring to with Appendix B. It is literally 100 formulas, I'll call them, for solving integrals. They break it up into like kind of groupings of similar forms, which is very helpful. I think it's like the first 40 maybe are algebraic. Let's see, it's still algebraic, still algebraic. Okay, the first 45. The first 45 are algebraic. From then on out, it's mostly trig identities and trig functions from pretty much all the way down to, yeah, then your inverse trig. Okay, E and ln come in at the end. Hyperbolics, we don't really discuss those a ton. But you can see these are all, look at that. I hesitate to use the word shortcut because I feel like then you'll be like, oh, I don't have to do anything. Not quite the case, but helpful pushes in the right direction for how to solve some of these integrals. So, all right, let me get rid of that and let's get back into it. So let's take a look at how we utilize this table in action. Oh man, is my recording window all out of that's weird. Okay. Oh geez. Now I'm all over the place. What is going on? I have no idea. I guess because that window is a different size. Now my recording's all wonky. All right. Yeah, I don't know what happened there. Oops. All right. Anyway, okay, but sorry about that, guys. How about that? There we go. All right, that looks good. Just move this down. No, it makes it move out. Okay. Aspect ratios and all that. All right, whatever. There we go. Okay. Let's actually get into this and see what it looks like. So I'm going to take a look at a function and how we solve this. I'm going to show you two different ways to approach this. So let's take a look at an integral here. Here's what we got. So let's go the integral of 1 over x square root of x plus 1, all right, dx. So there's an integral. That is one that I don't know how to solve off the top of my head, right? U sub doesn't really look like, I mean, U sub maybe, because you could U sub the root x plus 1 or x plus 1. Then you'd have to solve for x to sub the other one. Dx would sub out because your first derivative is the first order. So U sub might be able to do something to change that around, but it doesn't look like a direct solve. Integration by parts doesn't look great either. It's not any of our inverse trig functions. It's not a trig order one. Partial fractions maybe, if we could complete the square. I don't know. Doesn't look like a great one for anything we've really discussed so far. So let's take a look at how this tables approach works for us. It's hard for me to say tables. So the way I approach using the integration tables is I try to rewrite this in the form they use. So where we have a function u, and then everything else is in terms of constants. So that would be a and b, right? So my first try, or my first attempt at this, what I do is I just set x equal to u. So I would rewrite this like this. So I would say the integral of 1 over u. I gotta start using my tools better. Look, I can actually draw straight lines. Oh, I drew an arrow. I didn't want that. Let's try this again. There we go, straight line. 1 over u square root of u plus, and then here it's going to be a, because that's going to be my constant, right? That's all. So, and then du. So this is, if there is a table, if there is a formula for solving this integral up here, it will look like this in my table, right? So this is my problem. Excuse me. Then this is what I'm looking for in the table. So I will now pop over, see if I can do this again without messing up my screen capture deals. Nope. There we go. I will now pop over to my integration table. Yeah, this messes up my aspect ratio. It's all good, though. I don't know why it's not the same. There's the same size window. Weird. Okay. So I will now pop over to my integration table, and then I'm looking for, let me see if I can make this a little bit smaller so you can still see the formula. There we go. Yeah. So, too far. So I'm now looking for what I drew over here table. So my 1 over u root u plus a. I'm now looking for that in my table. So let me see what we can do here. So we have an forms involving a plus bu. I want that, but I want root that. So let me see if I keep going down here. Here's forms involving quadratics. Okay, so forms involving root a plus bu. So this would be kind of more in the ballpark of what I'm looking for. My b value in this case is 1 because I don't really have a coefficient on my u, but I have an a plus u in my function. So let's take a look at these. So 17 here actually looks like a pretty good fit, right? Like I said, our u is our b value is 1, and I wrote u plus a. This is a plus u, but I mean this basically fits what we have. So let me grab this, and I'm gonna pop over. I'm gonna pop back over to my OneNote here, but I will paste that in here, and then I will turn off that other screen. Let's make this a little bit bigger. So just turn that off. There we go. All right, so we're back at it. So if you look at this, so table 17 or formula 17 has the integral of 1 over u root a plus bu du equals, and then it gives us two formulas depending on whether a is positive or a is negative, right? A is positive is the top function, a is negative is the lower function here. So we have a case where our a value is 1. So if we could fill these in, right, if we wanted to, next to here. So u is just x, and a is just 1. And then even if we want to go farther, our b value is also 1, just based on, because the formula here has b's. So we didn't know at the time that we would need a b, but you could always put a b on the u if you want. Whenever you put a u, you could even put one here if we wanted. But either way, this sums us up pretty good here. So what we're gonna do is, since we have let's see if this will rectangle. Oh, nice. Since we have an a value being greater than 1. Oh, there we go. Ta-da. We have an a value that's greater than 1. We're going to use this top equation here. So let's write that out first, right? Just so we make sure we're doing the right one. So we got 1 over root a. Oh, no, the whole point of this is there's no more integrals. So ln of root a plus bu minus root a, gotta extend that radical there, all over my straight line, root a plus bu again, all over, plus root a, and then that wraps up there, and then plus c. So that's what we got. So now it's just really fill in the blanks here. So once again, u is going to be x, a is going to be 1, b is going to be 1. So we got 1 over root 1 ln, radical there, square root of 1 plus, I'll leave out the b for 1, I'll just drop the b's, but u is going to be x, and then minus root 1 all over, same thing, 1 plus x again, plus radical a, close that absolute value, and then plus c. Oh, I wrote a there. Sorry about that. 1, right? And then finally we can clean this up. So I'm going to go back up here and grab my original equation and say, oh, thought that was going to come down. Didn't quite do what I wanted, but there we go. So we can say that the integral of 1 over x radical x plus 1 dx is equal to 1 over 1 is just 1, so that's cool. So we got ln of, can't really do much with that, 1 plus x, and that could be, I mean, it's x plus 1, 1 plus x, it's the same thing. But root 1 is just 1 over 1 plus x plus, and then same thing, root 1 is just 1, close parenthesis or close value, plus c. Cool, cool, cool. So, I'll tell you a couple things. One, you could have done that integral without Formula 17. It is possible to do all 1 to 100 of those. Maybe not, we may not have covered how to do like the hyperbolics yet and stuff like that, but all the algebraic ones, 1 through 45, I promise you, you can do all of those without these shortcuts. Like using the techniques we've already learned. So just using the techniques we currently have, you are capable of doing this. Now, that being said, this is way easier, way quicker. Caveat to that, you will not have access to these tables all the time. You know, that said being like tests and stuff generally. We'll see how that goes for this class. Most likely I would say no, but it's up for discussion. But yeah, it is. These are literally just common. I don't want to say commonly used because how often does anyone integrate anything like this? But these are just essentially shortcuts doing a bunch of that work for you. Like it may take a page and a half to go from 1 over x radical 1 plus x to, or the integral of that, to the final solution of natural log of blah, 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 blah. So you could do it with practice and patience and you know, not breaking any math rules, following the correct steps. You can get there. This is just a nice shortcut. And really what it does, like I said, it takes away that having to figure out which step to do next. That's really the key of where it saves you a little bit there. So, all right, let's actually, so let me show you another approach to this this same problem here. So, what you could do, and I don't know, I don't mind showing it because I like the you'll have to do it in many cases, but what I'll say is I really like, I don't say my method, but just trying to find a table variation right away. Because if it's already done, if the work's already been done for you, why do more work? Like this formula 17 in the table basically matched exactly what our problem said straight up. So like, cool, you're pretty much done. um, However, they won't all be like that. So like in many cases, if we were to jump back into this, like what you might have to do is like let's say maybe we don't have access to our tables. Maybe we don't have them at the start of the problem and magically they appear midway through. We want to start trying to work this out. So like I said, taking a look at this, I mean I could see trying a U sub because I don't really see another great way, and a U sub should simplify it a little bit. So if I U sub this, and I just do my radical x plus 1, you could just do x plus 1 if you wanted, but uh, it's up to you. And then my du, so this is where it's going to get a little tricky. So I'm going to get 1/2, right, and I'm going to just rewrite this as 1 plus x, or x plus 1 to the negative 1/2, right? Whoa, why did I draw 2 slashes there? That's weird. To the negative 1/2 dx, right? You can see you're not going to get a direct substitution here, because if we were to sub the dx back in, we'd still have x's in our equation. It would be a whole mess. You can try it out on your own, but I'll show you two things about this. So one, since we have this lone x in our function anyway, we're going to have to solve this equation for x, because we're going to have to do that kind of substitution. So if we rewrite this, this could obviously be rewritten as x equals u squared minus 1. So that'll take care of our lone x there. And then, I don't know if you guys have ever done this before, but you can actually just take the derivative of this equation instead of this one, and you'll end up in the same spot, but it's way easier. So if we just take the derivative of this, we would just get dx equals 2u du. And you're done. And then this will direct sub into that, and we'll be gold. However, just in case you didn't know, these two are equivalent as well, right? Because if you look at this, if we work over here, let me grab where's my marker? There's my markers over there. Let me just write this in a different color here, just as an aside. So if you think about this, right, this little thing here, 1 plus x to the negative 1/2, that's really equal to 1 over u, right? Because u is the square root of 1 plus x. Yeah, the square root of 1 plus x. So 1 over the square root of 1 plus x is 1 over u. So if you rewrite that, you think about it as, so it would be du 1/2, 1 over u dx. You move stuff around, you end up with 2u du is equal to dx. So just a shortcut. They both work the exact same way. You do you however you want. So okay, so let's get back to substituting this. So obviously we have our 1 plus x is equal to u. So there's our 1 plus x. And then we have x is equal to u squared. I'm kind of messing up what I underline. I'm changing it up. Sometimes I'm underlining the x, sometimes I'm underlining the u. And then we have this 2u du for dx. So I guess what I should really underline on this one is I should really underline my u value, because that's actually what the substitution is going to be. So all right, let's see if we can make this convoluted substitution now. So we have the integral. 1, that's going to be the same over. So now x is equal to u squared minus 1. So u squared minus 1. And then root x plus 1 is just going to be u. So that's a nice easy one. So that's just my u. And then finally, dx, either way, here or here, dx is equal to 2u du. Cool. All right. So we can do a bunch of simplification here. There's a ton of terms to combine. We can divide some stuff out. Actually, I guess it's pretty simple. It's a pretty quick one, actually. U divided by u is 1, and then we can just move the 2 out in front here. So then we're left with 2, the integral of 1 over u squared minus 1 du. So doing that u substitution and doing a little bit of simplification now we already have a integral in the form, our u form, right, which would kind of be how we would look in our tables. So the reason you can do this, like let's say all of a sudden, now we have a table we can use. The other approach to this would be, once again, u sub's not going to work on this. Integration by parts, maybe. Honestly, I would think this would be a partial fractions, because this is a difference of squares. So you have u squared u plus 1, u minus 1, then you partial fraction that. That would probably be the road I would go down at this point. But let's say all of a sudden, oh, someone's like, hey, did you see Appendix B in the book? Check this out. So we pop over. Oh, I keep clicking the wrong one. We pop over and now it's in the way. Moving everything out of the way. There we go. Let's say, yeah, move it down here. So if we have that, so now we're looking for something in the form. Ignore the constant out in front. That's not going to change anything. But we're looking for something in the form of 1 over u squared minus 1, right? Or plus 1, because it's the 1 is the a value essentially, so it can be positive or negative. But let's see, so we want u squared, so this is only u to the first, so these aren't going to fly. This one's a full quadratic, so that's probably not going to be where we're looking. These are radicals, probably not great. Here we go, down here. A squared plus or minus u squared. So that's what I was just talking about, because a squared would be 1. Okay, so we're looking for, I think this one here, 24, looks pretty good, right? U squared minus a squared, because 1 is 1 squared, so that's cool. And I think that fits our form pretty well. So let's copy and paste this. We'll send this back over to our document and wrap up this problem here. So do that, and I will turn that window off. There we go, and we're back. So, whoa, too much. Whoa, too much. So, let's take a look. So now we have 1 over u squared minus a squared, right, where our a value is just 1, and u is literally u in this case, and that's really the only substitution we have. Yeah. So, right, they just factor the negative out here. This intermediate step doesn't really apply to us. Basically, just if we had 1 minus u squared, it would be the same thing. We would just have to factor a negative out. That's all. But it looks like it is 1 over 2. Our a value we said is 1, right? And then, well, so one thing I'm going to do is I'm going to put the 2 out here before I forget, because this 2, right, this 2 out here is still here, because we're just solving for the integral. So, 1 over 2 times 1, natural log of u minus 1 over u plus 1, close it up, and then plus c, and then I guess I could have put the plus c outside. Either way, but then if we take a look at this, obviously 2 divided by 2 is 1, so that's pretty cool. Let me grab some more space down here, and then we're left with natural log. Yeah, I know you guys are going to harass me for my oh, that's even worse. I can hear you guys now taunting me. So we would just be left with u minus 1 over u plus 1. And then finally, we're not looking for problems in terms of u, right? If we remember, u is equal to the square root of x plus 1. So we have to substitute that back in. So finally, we would end up with u ln, x plus 1 minus 1 over the square root of x plus 1 plus 1 plus c. Ta-da! And I really hope, I'm pretty confident that's what we did with the last one. If we go back up here, yeah, so you can see we have the natural log of, I wrote 1 plus x. Okay, 1 plus x, x plus 1, same deal, but the radical minus 1 over the radical plus 1. Ta-da! Math. Pretty cool, right? Once again, you may be asking, why do all that work? Like the second way, like why do that use substitution? The first way was way easier. Yeah, in most cases, if the integral already follows a form that you can find in the table, I highly recommend just doing it this way. I think it's significantly easier. However, that's not always the case. Sometimes you'll have stuff we'll have to move around a little bit, and then you'll see this doing a u substitution or doing some kind of other approach prior to checking the table is sometimes necessary. So let's take a look at another example. Okay, excuse me. Let's jump back into the next kind of technique here. It's called a reduction formula. So what you see, what we can do sometimes, reduction form. I don't know why I'm even writing this. I'm just talking. But sometimes what you see is, so we have an integral complex integral, right? F of x is a crazy function we can't handle. It's not even necessarily directly in the table, but what we can see, excuse me, what we can see is it can be broken up into maybe a simpler function plus the integral of another function. Right. Sorry. So I said not in the table. Like the table. Sorry. The tables give you this formula. Sorry. That's what I'm trying to say. So we take a crazy. I don't want to say crazy. We take a complex, not easily solvable integer, and we then turn it into another function of x plus another integer. Now this integer may still be challenging. Like we may still have to apply other techniques to it. Or maybe using the tables again for another simplification. It's not necessarily one-stop shop that all of a sudden I get this and then this is power rule and that's super easy and really nice. It's not always like that. But like I said, in many cases you may still have a complex integer here, or integer. Have I been saying integer? You may still have a complex integral here that we may still have to, do a bunch of work on to get to the bottom of, but still better than whatever f of x was. That's kind of the goal. Kind of very similar to when we use integration by parts, right? Well, this is actually the form integration by parts follows. When we get this, we get right? This is uv times the integral of v du. Sometimes that integral of v du doesn't solve right away. We may have to use other techniques, inverse trig, partial fractions, yada yada, to solve it. But it's still hopefully better than f of x and at least moving us in the right direction, right? So let's take a look. Let's take a look at this. I'm actually going to pull this one, this example straight from the textbook. I know I don't do that a ton, but it's kind of convenient when I'm working online here and just have it right next to me. So let's take a look at example 4 from the textbook here. So we have this integral of x cubed sine x dx. I think we've done similar ones where we've been able to use integration by parts to get to the bottom of this pretty quickly. I think that was just x squared though, because then dx is 2. Maybe not. Maybe it was just x sine x or x cosine x, because right now if you tried to do even an integration by parts or a u sub here, you'd still have an x squared. I guess a u sub would have x squared. Integration by parts, you'd still be okay, but either way. We could get to the bottom of this. We could do a whole mess of stuff, but let's take a look at using some of these formulas in our tables to see where we could how we could go, or maybe an easier, quicker way. So the book nicely actually summarizes some stuff for us here. So let's take a look. This looks like the first one that we can use here. So if I take a look at this, formula 54 in the tables. Right, it's going to be u to the n sine u is equal to negative u to the n cosine u plus n times the integral of u to the n minus 1 cosine u. Right, so let's take a look at what that means. So in our case, luckily, u is just x, so that's cool. Right, u is just x, because we don't have a function here, we just have x to the third. N is going to be 3, because n here is just the order of our function in the original integral, so that's cool. And then u du seems like we're pretty good. So that's all we need to know. So let's just take this from the right of the equal sign and fill some stuff in. So we're going to have negative x to the third cosine x plus, so n, which is 3, times the integral of u to the n minus 1. So this is where we get a little bit simpler, right? We're going from a third order to a second order. So x squared cosine x dx. Cool. Okay, so like I said, I would take that just because we went from x cubed to x squared. That's a win for me, right? That's going to be a little bit easier for us in general. Like I said, we're using these tables, so we're taking a very specific approach right now. But if I was, having to brute force this or just throw stuff against the wall until something sticks, you're almost always going to want to deal with lower orders. It just makes things easier, right? For u sub especially, because it makes u sub a more viable option in most cases. Not really here, but yeah. Even integration by parts, obviously a lower order is going to be better because then you'll have a lower order on your integral and all that jazz. But like I said, this is section 7. We're using tables, so let's take a look at just this portion here now, right? So let's see what do we got. See how nicely I can box this. Probably not. Oh, it rectangled. Cool. Okay, so we're not even actually caring about the 3 there. We're just We're just taking a look at this integral here. So we have the integral of x squared cosine x dx. So once again, we're using the tables. So if we pop back over to our appendix B, I won't show it this time. I'll save you guys the mindless scrolling. But we do have another formula here that fits the bill. This one's very similar to the previous one we just took a look at, but it's with cosine, right? Whoa. I wish I could make those like instantly the same, but it's gonna drive me nuts. But anyway, so we have this u to the n cosine u reduction formula, right? So, and like I said, this is just what's in the blue box. Heck, why don't I make it blue to make it clear? This is just what's going to be in that blue box up there. So once again, in this case now, our u is still just x. Now our n value is not squared. Our n value, however, is just 2. So if we write equals, u is x, x squared, sine x. Oh, the blue pen is thinner. I should have changed that. I don't like that. Sorry. Minus, once again, n is 2 now. The integral of u minus 1, which now is just x, sine x dx. Now, once again, I know we have done this. We could do this in integration by parts. We know we can, so that's awesome, right? But tables, right? Tables. We're doing tables, so let's take a look and see. Oh, wow, that was good. Look how good that rectangled. That was good. Give me credit. I demand it. So let's... I'm just kidding. You don't need to give me any credit, I understand. Let's take a look and see if we have a simplification for this. And simplification is probably not the right word, but we do. Look at this. So formula 52 gives us the integral of u sine u. It's just equal to sine u minus u cosine u plus c. Look, we're finally there. There's no integral in this. So you can see all the other two formulas we used still had integrals involved with them, and therefore no plus c at the end. This one finally, attempt number 3, we no longer have a integral in our equation. So what that means for us is this is just, u is just x, and that's really all we need. So this is just going to be sine x minus x cosine x plus c. Now we just have to work backwards and do all this in one equation, right? So let's start at the top. So what was our first one? The red was the first one. So I'll write it out. I won't be that lazy. So we got negative x cubed cosine x. So, no, I already missed the negative. Negative x cubed cosine x. Gotta scroll back up a little bit. Plus, then it's going to be 3 times everything here. Plus, and then we have 3 times our blue, which is going to be x squared sine x minus 2 times everything in green here, sine x minus x cosine x. We can close these parentheses and tack the c on the end. It doesn't really matter because the c is just a constant, so it doesn't really matter when you add it. That's just a constant, right? So let's clean this up. Let's make this a little bit neater, right? Nobody wants to see all those parentheses there. So x, this isn't going to change. Our first term is going to be x cubed cosine x, and then let's see. Let's work inside out here. So this is going to be minus 2. Minus 2 sine x plus 2x cosine x. So that'll take care of that. And then plus 3x squared sine x, and then minus, so these two would just need to be multiplied by 3. So this is just going to, this is just going to be 6, and so this will be 6 as well. Plus c. I may have messed some mental math up there, but I think I got it right. We'll see. So yeah, that would be an example of using a couple formulas for the same integral, right? We started up here with what? The integral of x cubed sine x, but then we kept on plugging away. And like I said, if these tables, this appendix B, appendix B is not your cup of tea, that rhymed. By all means, get really good at integration and rock and roll with these. That would make me so proud of you guys. But like I said, this can be pretty handy. It can save you a ton of time with some of your calcs. Once again, not going to save you. Like I said, what if you're walking down an alley and some guy takes your phone and is like, "Yo, I need you to solve this integral, pencil and paper, right here, right now, or I'm gonna keep your phone in your wallet." Right? You got to know the techniques. You got to know them, or you're in trouble in that alley. And that's a real thing that definitely happens. So just don't. I don't want you to rely too much on these, but they are they're definitely a handy tool for saving you a little bit of work on a lot of these problems, and definitely saving some struggle with knowing where to start. I'll give you that. Sometimes, like I said, sometimes when these don't follow the form directly, you still kind of end up in the same boat. You're still like, oh, what do I do? But usually it takes less steps to kind of get it into one of these forms than it does to solve the entire integral. All right, let's take a look at one more use or one more type of problem with this section. All right, let's jump back into this for one more example here. Excuse me. So once again, I'll grab a problem from the book because it's convenient. Copy and paste, right? So here we go. So let's find the integral of sine 2x. The integral of sine 2x over 2 plus cosine x. So there's going to be a specific, I'm looking to show a specific technique here. Oh, too far. When you're dealing specifically with sines and cosines, can work for some other things if you can do a correct u substitution, but you see it a lot with trig functions. I think this is going to end up being very similar to that problem we looked at the very end of class the other night, where I said do it for homework. I think it was like cosine to the fourth x or something like that. Similar technique here. What we'll need, where we'll actually, well, I don't want to spoil the fun. Let's take a look at this. So this is chapter 7 or section 7. So first thing, we should look and see if this, falls into a table, right? Is there a table for the integral of sine 2x over, well, I guess it would be like sine of bx over a plus cosine u du. I think I said x instead of u, but you get what I'm saying. Unfortunately, it's not. None of the trig function ones look this crazy, where you have a rational trig function. I don't even know if there's any rational ones in there. Maybe take a peruse through it and let me know. But I think the big thing, though, what you're going to notice is you have sine 2x and cosine x. That's usually going to throw a monkey wrench right there. If they have separate arguments and trig functions, it makes things way tougher because you can't combine, like you can never combine those trig functions into like a tan x. Not to say we're going to do that or anything, but also it makes the derivatives like more challenging and stuff like that. Like you wouldn't be able to set u equal to cosine x, because du would not equal sine of 2x, right? It would just equal negative sine x. You still could do u equals sine of 2x. Oh, no, I'm sorry, because it would still be cosine of 2x. Yeah, so you're not able to do any kind of u substitution or anything like that when you have different arguments in your sine and cosine. So that's usually where I like to start if I do have different arguments of my trig functions, especially, like I said, when you're alternating trig function, not you're alternating, but like secant tangent, like where you do have a derivative integral relationship between the two, so like a u sub would kind of be a possibility, and you're able to, obviously. And in this case, we have a formula, right, for sine of 2x. Sine of 2x is equal to 2 sine x cosine x. So that kind of solves our problem, like straight up right there. So that would be my first step. So that's where I would go. I know we haven't used any tables yet. Ridiculous, right? I'm just gonna throw the 2 out of here and rewrite this as sine x. Oh, terrible x. Sine x cosine x over 2 plus cosine x. Now we can just divide these cosines, right? Don't even get me started. If anybody did that, just get out of my class now. No, we can't do that because this cosine is being added, right? 2 plus cosine, that's an entity right there. You can't divide. Okay. You guys all knew that. I know. I was just messing. So now that we're here, now that we at least have the same argument on all the trig functions, right? So that's I think that's a great first step. Maybe check my tables again. Is this in the tables? Sine u cosine u over a plus cosine u du? Unfortunately, still no. um, however, and I don't want to say common practice. I don't know how common this is. Like I said, I don't do this kind of math every day, but when you're dealing with a complex integral that has sine and cosine in it, a lot of times what you can do is, and it's I was gonna say beautiful. I don't know if beautiful is the right word, but it's pretty awesome. If you do a U sub, a lot of times you can turn this into a linear, or in some cases a quadratic, right? So uh, I'm gonna set my U equal to cosine strictly because I have a cosine in the denominator down here. So, because if I set my U equal to sine, I would still get the cosine dx for my derivative. However, I wouldn't be able to sub in. I would never not get a substitution for this 2 plus cosine in the denominator. So for that reason, I'm going to set my U equal to cosine. Right. So my U is equal to cosine x, and then my du, just regular old du, is just going to be negative sine x and then dx, excuse me. And then I like to write this as negative du is equal to sine x dx. So here we go. So let's take a look at the substitution now. So we have cosine x here, cosine x here. I got something stuck to my hand there. Excuse me. And then we also have a cosine x here, so those will be u's. And then sine x dx is right here. Sine x dx. So I'll actually just write this up here right next to it with the substitution. So I still have the 2 out in front. Nothing changed with that, right? But so cosine just becomes u, and then over 2 plus u. And then I have sine x dx just becomes negative du. So I'm going to have a negative out in front here on my 2. And then I have my du there. So now that looks like a way, I don't want to say, I really don't like using the term easier. I keep saying easier. Way less complex integral. It's really not. It just looks that way. We were able to eliminate, obviously, all the trig functions. But the nice thing is we were able to eliminate a term from the numerator, which is pretty cool. Like I said, I'm just always looking to simplify. I'm not always looking to get where I'm going in one step, but if I just simplify it a little bit each time, hopefully I'll get where I'm going. However, now if we do jump into the tables, this does look like an approach we can take. We have a linear u here in the denominator. Let's do this. So I know we already have the u here, but if we did want to take it and write it in table form, the two in front is really arbitrary. We're just taking a look at the integral, but we'd be looking for something like u, and then this would be my a, and then I'll write a b this time. I know I forgot to write a b last time, but my b value is just 1. My a value is 2. Du. So that's what we'd be looking for from the table. We'd be looking for u over a plus bu du. I think I said that right. There was a lot of letters there. It's actually pretty convenient. It's literally number 3 looks pretty much identical to that. If we take a look at our table, I know I didn't scroll to it this time, but I think you guys got the hang of it. But look at that, u over a plus bu du. Bada bing, bada boom. So I'll scroll down here. So like we said in our case, a equals 2, b equals 1, and do we want to do u yet? Let's just leave u alone for now. We'll just leave u for u. We'll do that substitution last. But so yeah. So I guess what we still have the 2. Remember, we still have the 2 out in front. So we're still going to have that 2, and then it's going to be the integral. So 1 over b squared. So 1 over 1 squared, and then we have 1 times u minus a is 2 ln. Probably don't need a straight line there. 2 plus u, excuse me, because b, like I said, I'm going to drop the b's. B is just 1. And then finally plus c. So I'm going to do a cleanup step real quick, and then we will do our back substitution finally. So what do we have here? So I'll just leave this 2 out here. This is just 1, so that's nothing. So we've just got u minus 2 ln 2 plus u, still times 2, plus c. And then finally, let's just write this real quick. 2u minus 4 ln 2 plus u. That's fine. Plus c. So that is our integral. Unfortunately, I don't know why I said unfortunately. We're not quite done yet. We still have to go back and take a look at what our u was, right? Our u was cosine x. So we still need to take and substitute back finally u for cosine x. So now what we would have 2 cosine x minus 4 ln of 2 plus cosine x plus c. Ta-da! I hope that wasn't too anticlimactic for you. But yeah, that's another approach. That's honestly, I know that it's in the table section, but that's honestly a good approach in a lot of cases. Being able to convert trig functions into linear, or I shouldn't say linear, I was going to say linear or quadratic. Really, just turning trig functions into algebraic functions. Trig functions are, especially trig integrals, are very rigid. There's not a lot of options. There's some options. There's not as many options as there are for algebraic functions. So being able to turn a trig function into an algebraic function is going to be super helpful. Most of the time, not all the time, right? But just the big things to keep in mind with this section. Like, tables are cool. They're not going to save your life, right? That's the big thing. And the other big thing is, like I said, literally all 100 of those tables, maybe not the last couple because we just haven't touched on them yet, because I don't think we even know what like hyperbolics are, or right, I can't remember what the last section of those are. But either way, some of the stuff I don't know if we've touched on mathematically yet, but 1 through 45 I know at least, and then even probably the trig ones. You guys could derive those formulas on your own with enough go get 'em energy, right? So don't become overly reliant on the tables. You still need to know your integration techniques. You still need to practice those techniques. But this is definitely a helpful tool to guide you in your journey up the mountain of integration. All right, guys. Thanks for checking this out. You know what I'm gonna say. Now it's your turn. Do some problems. Do some homework, and just get after it. All right, thanks, guys. I'll see you at the next class.